Hello, everyone. So today we're going to start chapter 3, load and stress analysis. You may wonder what is load analysis, what is the stress analysis. So I'm going to quickly go over the slides from the publisher. Let's look at these slides. This slide sounds familiar. Equilibrium condition. I took my statics class back 1989, more than 30 years ago. So this is what I learned from statics class. So statics is to study the system under equilibrium condition. So equilibrium condition means the system is motionless or has constant velocity. So under equilibrium condition, we can write these two equations. The first equation is force balance, means the sum of all force vectors on the system is 0 if the system is under equilibrium condition. All right, so this is our force balance equation. And the second equation we call is moment balance equation. Sigma m equals 0 means the sum of all moment vectors acting on the system is 0. Keep in mind, here we call it force vectors and moment vectors. So moment vectors means they have x, y, z direction. Right? So you can break down the force balance equation into 3 equations in x direction, y direction, and z direction. Right? For example, you may write sigma fx equals 0, sigma fy equals 0, or sigma fz equals 0. Right. So similarly for the moments, it is a vector. Right? You can write sigma mx equals 0, sigma my equals 0, and sigma mz equals 0. So moments about x-axis, moment about y-axis, and a moment about z-axis. Right. So those are 2 most important equations from statics class. So I don't know when you took your statics class, but if you forget, that's fine. I just need you to remember these slides, these single slides. So that is loads, force, moments. We can find the load, find the moments, find the force through the statics. And stress. We just learned the stress from solid mechanics class. So when you talk about the stress, there are 2 types of the stress. One called normal stress, sigma. And the other one is tangential shear stress, right, which is tau. So normal stress is normal to the surface, and shear stress is tangent to the surface. If the normal stress acting outward the surface, occurs tensile stress. If the normal stress acting inward on the surface, occurs compressive stress. And also tensile stress, we use a positive. Compressive stress, we use a negative. And stress, the unit is a PSI or Pascal. So depends on what type of units you use. Well, we learned a lot of the stress. Again, as I said, machine design class is more like a stress analysis class. So we have to calculate the stress of the mechanical system, mechanical components under different types of the loadings. So most of your time is used to calculate the stress. Well, for the stress, We have two types of stress. One is uniform distributed stress, or another one called non-uniform distributed stress. So uniform distributed stress, for example, if you look at the tension or compression, also called axial loading. So under axial loading, the normal stress sigma equals F over A, and F is the axial loads, and A is cross-section area. Right? F is a tensile load or compressive load. And A is a cross-section area, depends on the dimension. Right? For example, if you look at the bar, usually we know the diameter can calculate the cross-section area. Or rectangular shape, and you can calculate cross-section area if you know the length and width. So this is under tension or compression. Under the direct shear. So what does it mean, direct shear? It means I only have the shear force, V. There is no bending moment. I only have the shear. So shear stress tau equals V over A. So again, V is the shear force, and A is the area, the contact area, or cross-section area. So you can calculate the normal stress under tension or compression, and shear stress under direct shear. For tension, compression, and direct shear, they all end up with uniformly distributed stress. So if you look at cross-section area, if you pick up any points, and the stress value is the same. That's why I call it uniform stress. Another type of loading in your solid mechanics, I hope you still remember, pure bending. So let's say this is a beam. So let's look at this beam. Yeah, pure bending. So this is a beam, rectangular beam, is subject to bending moment M. Right, so we have one bending moment on the left-hand side, another bending moment on the right-hand side, M. So how do you determine the direction of the bending moment? We just use the right-hand rule. Right, so in this case, for this one, left-hand bending moment, if you use right-hand rule, and this direction is the direction of the bending moment. And for this M, on the right-hand side, if you use right-hand rule, right, so the direction of the bending moment is in this direction. Right. So under these two bending moments, the total result of the bending moment is 0 because the magnitude is the same, but the size in opposite, right, is opposite. So it calls pure bending. So under this bending moment, if you cut this beam, it's a summary here. What is the reaction bending moment? So if you cut this beam here, and the reaction bending moment will be the same, M, right, but it goes to opposite direction. Right, so in this case, if you cut this beam at different locations, the reaction bending moment is M, it's constant. Right. So this is a pure bending. So for the pure bending, the beam is subject to constant bending moments. If you look at the different cross-section area. So for the beam, we can define a neutral axis, which is X. So X-axis was called neutral axis. And XZ plane. So this is X direction, this is Y direction, and this is Z direction. Right. So XZ plane is horizontal plane. we call is neutral plane. So x here, and z is here. Z is here. So x plane we call is neutral plane. So neutral axis is coincident with centroidal axis of the cross section. So it's very important to find the neutral axis and neutral plane for pure bending case. So under the pure bending, the beam is subject to normal stress. Also, we call it bending stress, sigma. And the stress direction is in the x direction. So now if you apply the bending moment M here, right? And you can imagine that we have the bending stress in x direction. That's why I call it sigma x. Sigma x equals minus my over I. And m is a bending moment. So for pure bending, we know the bending moment is constant. It's fixed. And y is, what is the y? Y is, this is the y-axis, right? Y is the distance of the point to the neutral axis, right? So it's offset distance to the neutral axis. And I call second area moment about the z-axis, right? So it depends on the cross-section area. You can find the I. And y depends on the distance, right? For example, at the neutral axis, y will be 0. Therefore, the sigma x equals 0. On the surface of the beam, you can say y has the maximum value. Right? Let's say c. Right? C, y is maximum. And then the sigma x equals mc over I. So you can see that the sigma x varies linearly with the offset distance from the neutral axis. So this is a linear distribution. At the neutral axis, stress is 0. On the surface, it gets to maximum stress. It could be maximum tension or maximum compression. So here, if you bend this way, and the bottom of the surface, we have maximum tensile stress. On the top surface, we have maximum compressive stress. Again, as I said, compressive we use a negative, and tensile stress we use a positive. But the relationship is a linear relationship. So it depends on the offset distance y. And here, it give you what is the maximum bending stress. So maximum bending stress is where y is the maximum. So if y equals c, and sigma will be the maximum. So sigma max equals mc over I. We can define z. Z occurs as section modulus. Z equals I over c. So I depends on the cross-section area. C also depends on cross-section area. So basically, Z depends on the geometry of the cross-section. So you can rewrite this equation, sigma maximum equals M over Z, and Z equals I over C. Just to move this C down, you get section modulus I over C. So this is a normal stress under pure bending. So under the pure bending, we only have bending moments and only have the bending stress in x direction. There's no stress in y direction, z direction. There's no shear stress. So for the pure bending case. Now let's move to transverse bending. All right, transverse bending. So what does it mean, transverse bending? Transverse bending means the beam is under the bending because of the loads, and the loads could be concentrated loads or could be distributed loads. So let's look at this figure. So we have the beam, let's say this beam, and we have F1, F2, F3, right? Let's say 3 concentrated loads. And on the two ends, the left, we have R1 with reaction force. And on the right-hand side, we have R2, which is reaction force as well. So usually, we give you the concentrated load, F1, F2, F3. And you should be able to find reaction forces, R1 and R2. So how do you find reaction forces, R1 and R2? This is a starting point of the solid mechanics class. You need to find a reaction force and then calculate the bending moment, calculate the shear load, and then calculate the normal stress, calculate the shear stress. So how do you find R1, R2? Well, in this case, we need two equations. Right. If we have two equations, we can figure out R1 and R2. So we need to figure out two equations. And so here, well, if you look at the force balance in y direction, you can have F1 plus F2 plus F3 equals R1 plus R2. So this is equation 1. How do you find the second equation? The second equation, apparently you can use the x-axis, right? Because in x direction, there is no force. But we can choose, for example, the left or right as a moment center. So let's say if we choose this here, origin is a moment center, and then you can write the moment equation. So in this case, you know F1, F2, F3, and we don't know R2. So based on the moment equation about the origin, we can find R2, and then we can use the force balance in the y direction and find out R1. So I just described how to find the reaction force, R1, R2, based on the statics. Again, as I said, if you forget statics, it's fine. But you should be able to remember forever how to write equation, force balance equation, and moment balance equation. So we will know all the forces, F1, F2, F3, R1, R2. But in order to find the stress, we need to find moment, reaction moment, M, and also the shear load, V. So let's cut this beam somewhere here, location X1. Let's cut the beam location X1 here. And then after cut it, and then we take the left portion. So on the left-hand side, we have R1, and we know this distance is X1, and this is F1. And there are two reaction nodes. One is the shear, V. Other one is a moment, right? So shear, we call it a transverse shear. And moment, we call it reaction bending moment. There's no other type of the nodes. I only have the V and the M. So in solid mechanics, we ask you to sketch, I hope you still remember, how to sketch the moment diagram and shear diagram. So usually the bending moment M is changed with the location. So it changed with X. So at a different location, and the bending moment is different usually. Also the shear could be different. So this is very important skill. You need to know how to use FBD, right? For about diagram to determine and then apply the statics to find the internal shear force and also bending moments. Right. So how do you find a V and an M? Yeah, let me ask you this question. So how do you find V and an M? Well, we just use statics, right? Statics. So if you look at the force-wise, in y direction, we have R1 positive, F1 negative. And V, let's say negative, right? Downwards. Right. It doesn't matter. You put the V upwards or downwards. If you put upwards, that means you'll find the V is negative, which means it's downward. Right? If you put downward and you find the V is positive, which means your assumption is correct. So it doesn't matter. You put the V is upward or downward because eventually you get opposite sign. Right. So use a force balance in y direction, you can find the V. And how do you find the M, the bending moment, at this particular location, cutting location? Yeah, this is a question. How do you find the bending moment, M? Well, in order to find a bending moment, M, because we don't know the V, right? It creates some problems. However, if you choose this point, this location as the moment center, so V is through this point, therefore the moment produced by V will be 0. Right? So in that case, we don't worry about V. Right? So in that case, if we choose the cutting location here as a moment center, and you can write the moment equation, right? And this M will be counterclockwise, which is positive, and F1 is going to produce bending moment counterclockwise as well, right? So F1 times this distance, right, positive. And then look at R1. So R1 is going to produce the bending moment clockwise, which is negative. So minus R1 times X1 equals 0. So we use a moment equation. You can find the M. So this is very important. Every time I give you a test problem or homework problems, what is the most difficult? Difficult is sketch the FBD and then use a statics to find moments, find the shear. Apparently, if your shear, your moments, it's wrong, and then all the stresses are wrong. So this is very important. It's a difficult job. Don't think it's an easy job, especially when you look at practical problems. Sometimes it'll be hard to understand, right? You need to translate the practical problems to FBD and then find all the nodes. Right, so this is under concentrated loads. Yeah, if you look at the shear, so this is a positive shear, And this is negative shear. Right? So if you cut the beam somewhere here and take the left portion, we'll assume this go upwards is a positive and go downwards is a negative. Right? Again, as I said, just convention. I mean, it's just depends on who is making the rule. Right? But we just use constantly follow these conventions. This is a different type of the transverse loading. So in this case, we have distributed load. So usually distributed load is a little bit harder compared to concentrated loads. In order to describe distributed loads, you have to define a load intensity. So load intensity, for example, Q, we use a Q. Q is function of the X. That means at a different location, load intensity is different. So for example, here, at the starting point, the load intensity is 0. There's no load. On the ending point, the load intensity is 0. So load intensity is not uniform. Apparently, the load is not uniform. So the core is distributed load. For distributed loads, because the Q is a function of the X, so basically we can have those equations. Well, those equations sound familiar. So let's look at the shear, transverse shear. V equals dm over dx. Right. So if you have the bending moment, you take derivative of bending moment with respect to x, you'll get a shear. If you take the dv over dx, you'll end up with q, load intensity. So usually, in a particular application, we give you the load intensity. We give you this function, q. And then you can find the v. So how do you find the v? In order to find the v, you just do integration. So you do integration. So we have VA to VB, right? From point A to point B, dV equals VB minus VA. And then from X to XB, right? So if you do integration one time, integrate from A to B, and you'll get a V. You get a shear. In order to find the bending moments, you need to integrate it twice. So because dm, right, second order, dx2 second order equals q. So you just do integration twice, and you'll find the m. It's not difficult. And then you apply the boundary conditions. Right? So for example, in this case, what is the bending moment at this location? And what is the bending moment at this location? Well, at the two ending points, the bending moment is 0. Is 0. So you know the boundary conditions, and then you apply the boundary conditions, and then you can find the constants. Anyway, you're supposed to know all those tricks, so your solid mechanics. If not, please go back and read the textbook. And again, as I said, this class is built upon the solid mechanics. So, and then after you find the bending moments, how do you find the transverse bending stress? right, sigma stress. So basically, we use the same equation. Sigma, the bending stress, equals negative my over I. Well, m will be changed with x in pure bending moments. The bending moment is constant. But in transverse bending, the bending moment is changed with the x. This is the difference. So pure bending and transverse bending, the difference is in transverse bending, the bending moment is changed with x, but it's not constant. Well, let me just remind you, why do we have the negative sign here? So you can say the stress sigma x is in the opposite direction of the y, right? If you look at top surface, y is a positive, and then the stress will be negative, compressive. If y is negative, and then stress will be positive, which is tensile stress. So you can say under the bending and above the neutral axis, we have the compressive stress. Below the neutral axis, we have a tensile stress, right, because this negative sign. So here, you use the same equation. Right? The difference is m is not constant. Another difference is there's a shear stress. In pure bending, there's no shear load. V is 0. Like you have a beam under the pure bending, you cut at different location, and V is 0, and m is constant. So that is the simplest case. In transverse bending, we'll always have the bending moments. We'll always have the shear force. So bending moment is going to cause the normal stress, and shear node is going to cause the shear stress. So this is a normal stress because of the m. How about the shear stress? Right, shear stress. So shear stress, we use this equation, transverse shear. Tau equals VQIB. And Q equals first moment of the error. And I is a second error moment of the error. So this is a Q, VQIB. Let me give you this example. For example, this is a rectangular beam. The cross section is a rectangular. And we calculate the B. I'll calculate the shear stress. Tau equals VQIB. V is the shear force. You just use a statics, use FBD, find the V. And Q, well, the first moment of error, right? So we can find the Q. Right? This is error, shaded error from C surface to Y, to the particular location. So you look at this area, So say the Y value is changed from Y to C, Y to C. So we go through this. This is how we find the Q. So Q equals B over 2 C squared minus Y1 squared. C is a maximum height, let's say. And Y1, well, on the neutral axis, what is the Y1? Neutral axis, Y1 will be 0. Well, you'll find out if Y1 equals 0, and the Q will be maximum, right? Because this is the minus Y1 squared. If Y1 equals C, for example, Y1 get the maximum value, which is C, and then you end up Q is 0. So this is a little bit out of the expectation. On the surface, when Y1 equals C, Q will be 0. Therefore, shear stress will be 0. So what does it mean? Means on the surface, there's no transverse shear. Shear stress is 0. Let's look at neutral axis. Neutral axis, which y1 is 0, and then you end up with Q is a maximum. Right? If Q is a maximum, then you have maximum shear stress. So this is kind of distribution of transverse shear stress. On the surface, the shear stress is 0. On the neutral axis, shear stress is maximum. But if you look at the normal stress, right, bending stress, the neutral axis is 0, and on the surface, normal stress is maximum, right, in the opposite way. So this is very interesting. On the surface, we have maximum bending stress and 0 shear stress. On the neutral axis, we have 0 normal stress, but we have the maximum shear stress. So particularly for rectangular beam, and we can find a tau maximum equals 3V over 2A. Again, V is a shear load, A is a cross-section area of this rectangular beam. Well, it depends on the geometry of the cross-section. And the shear stress is a little bit different. So this is for rectangular beam. The maximum shear is 3V over 2A. If you have a circular beam, and maximum shear is 4V over 3A. And this is hollow one, right? Hollow thin-walled circular. And you'll find tau maximum is 2V over A. And this is the I-shape, structural I-beam. You can see the maximum shear. Well, this is a stress distribution. This is a stress distribution. It's pretty much, right? But of course, we're not on the surface. On the surface, the shear stress is 0, right? So it's pretty much the same, pretty much the same. So it depends on the cross-section area. And the transverse shear stress is different. But when you do the design, the machine component design, usually transverse shear stress plays less role compared to normal stress. So in most of the cases, we just ignore it. Right? For example, when you design the shaft, transverse shear stress may just play 3% of the role, and normal stress may play 97% of the role. Right? So in that case, most of the cases, we just ignore the transverse shear stress. However, if the beam, the shaft is a short shaft, and transverse shear stress is more significant. So depends on the length, right? The short shaft or long shaft, and the role of the transverse shear stress in the design is different. And we'll give you more details in the future. Well, another type of the loading we call is torsion. Torsion. This is schematic for torsion. So we have a circular shaft, circular bar, is subject to torque T. So on the left hand side, well, if you use a right-hand rule, what is the direction of this torque? So it goes to this direction, negative X direction. And on the right-hand side, and T go opposite way. And direction of this torque go positive X. So eventually, this shaft is under equilibrium condition, because this torque is positive and this torque is negative. and subject to torsion. And we can find theta. So theta, of course, angle of the twist. So what does it mean theta here? So under this torque T, and this bar is twisted. Right, it's twisted. And the twist of the angle is a theta. Usually the angle is very small, actually. A long time ago when we did experiments, it's very hard to measure this angle, very small. And this angle equals TL over GG. T is external torque, and L is the length of this bar. G is a shear modulus, and J is the polar moment. Well, because the torsion and shear modulus is more important. That's why here we use a G, shear modulus. So I hope you still remember this equation, how to find the angle of twists. And how do you find the torsional shear stress? Tau. Torsional shear stress equals T rho over J. T is a torque, and rho is the point of interest to the center point, right? Or center axis, which is here, and over polar moments. So in this case, you can say at the center point, rho is 0, so therefore shear stress is 0. On the surface, and we have maximum rho, so we have the maximum shear stress. So you can say under the torque T, the shear stress on the cross-section area is not uniform. It's non-uniform. It's non-uniform. We talk about the direct shear. Direct shear, we have uniform shear stress. But in the torsional case, the shear stress is not uniform. On the surface, outer surface, we have tau maximum. Tau maximum equals TR over J. So on the outer surface, the rho equals the radius of this bar. So it's maximum shear stress. And so now, let me just give you some kind of the sorts. So if you look at the actual loading, tension compression, and we said the stress is uniform. If you look at any point on the cross-section area, the stress will be the same. So when you do the design, it doesn't matter where you pick up the location because the stress is uniform. For the pure bending or transverse bending, and we know the maximum stress, normal stress, is on the surface. And the maximum shear stress, transverse shear stress, is at the center points. Right. For the torsional case, and with our maximum shear stress is on the surface, and center point shear stress is 0. Right. So based on what I told you, so when you design any mechanical components, and from the common sense, you feel like the surface point is important. Why? Because under the bending moment, under the torsion, most likely they have maximum normal stress and maximum shear stress. So you have to be very careful about the surface, right? So when you do the mechanical design, you need to find where we have maximum bending moments, where we have maximum torque, and and then most likely in that particular location end up with maximum normal stress and maximum shear stress, which is the dangerous location. So in the solid mechanics, you learn axial loading, you learn pure bending, you learn transverse loading, also you learn about the torsion. So in most of cases, they are combined. You can combine axial loading, you can combine bending, with a bending or with a torsion, all three of them, they're all combined. So under the combined loading, you just calculate the stress individually, and then just adds up together. So this is how we handle combined loading. You just calculate them separately, and then adds up together. That is your final stresses. Another thing here, I have two more slides here, is about the power, speed, and the torque. When you design a mechanical system, usually there is a power requirements, how much power you need. So the power, H equals T omega, right? Power usually is given by the application, the design application. And T is a torque, right? Applied torque. And omega is angular velocity. So you may use this, for example, most of the time, we give you the H, we give you the omega, and then you figure out what is the torque you need. Right? So you know the load, and then you can find the stresses, right? Find the dimensions. So this is in terms of watts, Newton meter, and angular velocity is rad per second. You may use different units. For example, here, T equals 9.55 Hn. H is power in watts, and N is RPM, revolutions per minute. Just keep in mind, if you use different units and equation is different. Right? So this is a relationship between the H and T and N, use US customer units. So again, I said, when you do the design, most of the time we give you power requirements. We give you the velocity, RPM, right? The speeds, the gear speed, transmitted power, and then you decide what is the maximum torque, minimum torque you need. So this is your starting point. Well, let me give you one example problem about the load analysis. So let's put it here, load analysis. Well, load analysis, you need to use the statics. As I said, statics, you must remember two equations. So we have sigma F equals 0 and sigma M equals 0. F is a vector, so we can write sigma Fx equals 0. So the sum of the forces in x direction is 0, and sigma Fy equals 0, and sigma Fz equals 0. Right. So you can write three equations in x direction, in y direction, and in z direction. Similarly, for the moment vector, we have mx equals 0, sigma my equals 0, and sigma mz equals 0. So moment about x-axis, moment about y-axis, and moment about z-axis. Right. So you get another three equations. So basically, for any statics problem, you can write 6 equations, and you can solve 6 unknowns. Right. So this is very important. You know how to write the force balance equation and how to write the moment balance equation. Also, we need to sketch FBD. Right. So what is the FBD? FBD is free body diagram. So based on the problem I gave to you, you should be able to sketch the FBD correctly. So based on the FBD, and then you can write 6 equations, and you can solve all the reaction forces or reaction bending moments. So this is the statics. And here's a quick example problem. So I just use example problem 3-1 from textbook. And you have the solution on the textbook, but I'm trying to go over this problem, make sure you completely understand how to solve this problem. So let's look at this problem. I just gave you 10 seconds. So let's look at this problem. Yeah, this is a gearbox. So inside of this gearbox, we have input shaft and AB and output shaft CD. And AB, we have one gear, gear 1, and output shaft, we have gear 2. So gear 1 we call is input gear, and gear 2 also can call is output gear, or gear 1 is pinion gear. Gear 2 is a driven gear. Right. So at the location AB, we have 2 bearings. So I have 2 bearings here, one here, one here. On the input shafts and output shaft CD, we have 1 bearing here and another bearing here to support this shaft. So input torque is 240 pounds/inch, and output shaft output torque TO is given here. And the velocity rotational speed is omega 1 for input shaft, output is omega O output. And the gear 1, smaller gear, R1 is 0.75 inches, and gear 2 is 1.5 inches. Right. So this is the problem. We ask you sketch the FBD of each member and determine the reaction forces and the moments at all points. So we ask you to find the reaction forces at A, B, C, D. Right. Well, first of all, we need to sketch the FBD. FBD. So what does it mean FBD? When you sketch the FBD, and so you need to pick up the member, right, you are interested in, and then take it out. So in this case, I will look at those 3 members, the box, right, the box. This is a gearbox. Right. And another member is the input shaft and output shaft. Right. So we need to sketch the FBD for gearbox, input shaft, and output shaft. So we just take out those members from the system. Apparently on this system, you have a couple of components. Let's say, we have a box here. Actually, this box also have other components. They have a cover here, and they use boats to collect the cover and the box. There are some details And also on the input shaft, AB, this is a shaft, and also we put a gear on it. You can put two members together. In this case, we put input shaft and a gear. And also, there are reaction forces and bearing A and bearing B. And for the output shafts, we take out the shafts and also the gear 2, together. And then we need to find out reaction forces and gear C, and the bearing C and bearing D. Right. So this is FBD for gearbox, FBD for input shafts, and FBD for output shafts. And then we need to find the force here at A, at B, at D, at C. So this is a question. So let's look at input shaft. Right? This is option. So we can set up the coordinate system like this. This is the x-axis in the shaft direction. And this is a y direction. This is a y direction, horizontal. If you use a right-hand rule, and this will be a z direction. Z direction. Z direction. Well, in this case, we have some good news. In the x direction, for example, reaction force at A, we know RA in x direction. The reaction force should be 0. There's no force in the shaft's direction. And RB x equals 0. So we just need to find out RAY and RAZ, RBY and RBZ. The same thing here for bearing C. We can say RCX equals 0 and RDX equals 0. So in the x direction, the shaft's axis direction, there's no force. So we only have RDY, RDZ, RCY, RCZ. And you may ask a question. I don't know, how do you specify the direction of RAY, RAZ? It doesn't matter. Again, as I said, you can assume one direction, make an assumption. If you find out RAY is a positive, that means your assumption is correct. If you get RAY is negative, that means the opposite direction. So it really doesn't matter when you make the assumption. So now let's look at the input shaft. Let's look at the input shaft. Let's look at the input shaft. This is the input shaft. And TI is input torque equals 240 pounds F inch. And so now reaction force here. And also you need to find the gear force. So input shaft AB is on the top, and output shaft CD is below the input shaft. Right. So this is at the contact point here, this location, there's a gear force. So let's look at the gear force. We'll talk about the gear force in chapter 13. But I just gave you an idea. For the gear force has two components. One is F component. So F is in the tangential direction. Another one is in a radial direction. So the gear force is the resultant of tangential direction force F and the radial force N. So if you look at the gear force, so basically equals F square plus N square, square root rho. And this angle we call it the phi. Phi is a pressure angle. Pressure angle. When you buy the gear is usually is a standard part. So the pressure angle is pretty much standard. Right? So phi usually you can get like a 20 degree, 25 degree, depends on what type of gear you get. So here I just say phi equals 20 degree, standard gear. Right. So based on the gear force and the pressure angle, we have the relationship. So let's say this is a phi. So we have tangent phi equals what? Equals N over F. So therefore you can find the N equals F tangent, F tangent 20 degree, 20 degree. Well, if you look at the moment about x-axis, so let's put sigma mx equals 0. Right, this is the x-axis. Moment about x-axis, there's input torque Ti. Right. So let's put your eye look at it from this way, right? This way. So Ti is clockwise, right? So it's negative minus Ti. And this is Ay is through the x-axis, there's no moment. N is through x-axis, no moment. And F is going to produce moment counterclockwise. So plus F times the radius R1 equals 0, right? Equals 0. Equals 0. So you can get two equations. So we know the Ti, input shaft torque, and we know the R1. Right, so this is equation 1. This is equation 2. Right. So we can solve. Let's move it up. So based on these two equations, right, we can solve the F and N. So F equals Ti, right? F equals Ti over R1 equals what? Equals 240. And inputs shaft radius is 0.75. So equals 320 pounds F. Right. Therefore, you can find that N equals F tangent 20 degree. So N is 116.5 pounds F. So for the input shafts, we can find F and N. Right. But we need to find RAY, RAZ, RBY, RBZ. Right. We have four unknowns. Right. So how do we find four equations based on the input shaft? So you can use Fy, force balance in y direction, right? Force balance in y direction. in y direction. Let's look at y direction. Y direction is horizontal. We have minus RBY, right? So negative y minus RAY, negative y, and F is positive. So this is the first equation. Also, force balance in z direction, right? Z direction. So z direction we have minus RBZ minus RAZ, right, RAZ here downward, and plus N. N is going up, right? So this is positive. Okay, so that is a force balance, and then we can write the equation my moment about y-axis, right? Y-axis. So this is y-axis. So in this case, we'll find out. Let's look at the y-axis. So RAZ. Yeah. So let's set up the equation like here. Let's put a y-axis here. Y and N. Yeah, let's put it here. So let's put a y-axis here. This is our y-axis. About this axis. So in this case, if you look at a y-axis here, let's put our eye here. Right. Let's look at it from this way. So we have RAZ. This force is going to produce a moment. Right. RAZ times the distance will be 1.5 plus 1 inch, 2.5. Right. And also the direction will be negative, right, clockwise. And N is going to produce positive, counterclockwise moments, N times 1.5 equals 0. Right. So that is a moment about y-axis. Now let's look at the moment in z direction. Z direction. So let's put z here. Let's put a z here. This is the z-axis. Right, z-axis. So in that case, RAY is going to produce negative RAY. Let's look at from the top, the eye here. So 1.5 plus 1, right? And also F is going to turn this way, counterclockwise. F times 1.5 equals 0, right? Equals 0. So we have equation 1, equation 2, equation 3, equation 4, right? Equation 4. 4 equations. So you can solve for unknowns. So therefore we can get RAY. Yeah, I'm not going to go through the details, but I just gave you the answer directly. RAY equals 192 pounds F. RAZ equals 69.9 pounds F. And RBY equals 128 pounds F. RBZ equals 46.6 pounds F. Right, so that is input shaft. Now let's look at output shaft. Well, this is our output shaft. Well, we know the N, F to the gear 2. Gear 1, gear 2, the action reaction force. So we know N and F as well. And also we know the output torque, right? And we need to solve our dy, our dz, our cy, our cz. So we need to solve 4 unknowns, our dy, our dz, our cy, our cz. Right. So you need 4 equations. Right. So 4 equations and solve 4 unknowns. Right. So I'm not going to go through the details. Actually, I'm going to assign this problem as as our homework problem, and you can get more details. So, but I can give you the answer. Our Cy equals 192 pounds F, and our CZ equals 69.9 pounds F. And our dy equals 128 pounds F, and our dz equals 46.6 pounds F. Right. Anyway, so 4 equations, 4 unknowns. Practice your statics. 3. We need to find the forces on the gearbox. So, gearbox. We need to find the forces on the gearbox. So this is our gearbox. Apparently, you look at the force on the shafts and the force on the gearbox, the action-reaction force. So let's look at B. We have RBY, RBZ. So therefore here we have RBY, RBZ, just opposite direction, action-reaction force. Look at A, we have RAZ, RAY, and here we have RAZ, RAY, action-reaction force. And output shafts at D. D we have RDY, RDZ. Here we have our dy, our dz, and C we have our cy, our cz, our cy, our cz. Right. Action-reaction force. Right. And also, as I said, this is the cover of the box, and this is the box. So they're connected through the bolts, right. And you can imagine that when you apply the torque, you are trying to rotate this box, right? But this box is under equilibrium condition. So therefore, in that case, you can assume this box and the cover, right? They're under equilibrium condition. So under equilibrium condition, we can set it up the equation. Right. Set up the equation, the moment equation. So let's say this is the x direction, right. And this is a y, and this is a z, right. Z. So we can set up the equation. So sigma m x equals 0. Right. So because these moments, for example, this force, they form the force couple, and this force, they form the force couple. Right? So the force couple is going to produce the moments. So this go this way, this go this way, therefore we'll produce moments that way. All right. Similar here, this go this way, this go other way, you're going to produce a moment go that way. And in order to balance that, so we have to have the force. Right. Let's put a force R from the cover to balance this torque. Right. And there are 4 bolts here, right? So we're shown we have R here, R here, R here, R here, right? Usually the difference is very small, so you can assume maybe the value of the R will be the same. So based on the moments, we have, so if you have I here, right, you're looking from that way, this is going to produce this force couple clockwise. Right. This force couple is going to produce clockwise moment. So we have RBY times the distance between these 2 shafts, which is 0.75 plus 1.5. Right. The radius of these 2 gears minus RAY, and the distance is 0.75 plus 1.5. Right, so clockwise, plus R, the bolt force, the shear bolt force, and the radius will be square root 5 square plus 4 square. We give the dimension, right? This is 4 inches, and this is 5 inches, I think, this one. So 5 inches here. Right. So the center point will be here, equals 0. So in this case, the R equals 56.22. Right. So here we just make an assumption that all the R's that are equal. Right. So we have R. So we have RE basically equals RE equals RF equals RI, right, equals okay, and RA right, RA. So here if it's hard to say actually. Yeah. So there RH equals R. Right? They're the same. So you have an assumption. All right. So based on moment equation, you can find the reaction force, right, from the cover to this box. Right. So this is a very good example problem, and hopefully through this problem, practice your statics. And I'm going to assign this problem as one of the homework problems. So make sure you fully understand this. So based on this problem, you can say, in order to solve this problem, you have to properly sketch the FBD. You just take out the members from the system, and then sketch the right reaction forces. Right? And then you apply the statics, the 6 equations I introduced here, force balance and moment balance, to set up the equations and solve all the reaction forces. Right. And next step will be stress analysis. You calculate stress. For example, you may calculate stress in the shafts, right? But you need to find those reaction forces first. Right? And then you can calculate the shear force, calculate the moment, and then find the shear stress, find the normal stress. Right? So if your FBD is wrong, your statics, force equation, moment equation is wrong, definitely you'll get a wrong answer, for your stresses. Right? Okay, so that is load analysis. This is a very good example. Please read the solution on the textbook. And also I'm going to post these notes on the web course as well.